Thanks everyone for joining us on this Thanksgiving week. Sorry about the inconvenient timing. I probably would have held a break in these tutorials this week, but of course we missed the last 2 weeks, so I figured we couldn't really delay. We will continue again next week as well. So we did the 3 weeks on single particle analysis already. And the goal today was to move on to this subtomogram averaging tutorial. Then I expect we'll probably spend today and maybe next session on the subtomogram averaging tutorial, and then the week after that we'll move on to the Gaussian mixture model dynamics and flexibility stuff, and hopefully we'll manage to finish that stuff up before Christmas and wrap things up. The Gaussian mixture model tutorial doesn't actually exist yet. I need to write it. There is one that you'll find online if you look at the EMAN web page here. So if we look in tutorials, you'll see that there is somewhere down here, single particle analysis. Here you go. 3D variability using Gaussian mixture. So this is the tutorial that Muyuan wrote for the original version of the GMM. And it involves doing some stuff in Python, involves doing a bunch of stuff in the command line. There's now a GUI for doing the Gaussian mixture model stuff, which is reasonably stable now. So I'm going to put a new tutorial together for that. So you're welcome to try and follow this tutorial if you'd like, and you'll get some general information out of it. But if you do things via the GUI, it will be fairly different than what you see there. So I'll post it there, and I'll let people know when it's available, hopefully next week. All right, so the tutorial we're going to be doing today is the tomography workflow tutorial. It used to be 2 separate tutorials. There was a small version and a large version. Now I've integrated them into a single document. So it's now a single tutorial with a large option and a small option. The difference between the 2 data sets is the large version uses four fully sampled tilt series from this Empire 10064 data set. It's just ribosomes, a standard single particle prep of ribosomes, which was then collected as a tilt series. And then the small version of the tutorial uses 3 out of the 4 tilt series. The key point here, though, is that they've been downsampled by a factor of 2, so everything runs, about 6 or 7 times faster typically. I ran through the large version of the tutorial myself, just using my little Mac at home. It is possible to do this on like a 4 or an 8 core computer pretty easily. Although some of the full refinement runs may have to run overnight or something like that if you only have a few cores available. Obviously, we're not going to go through and wait for all of the steps when we're going through the tutorial here. Hopefully, all of you are already familiar with what I just said and have already gone through these tutorials yourselves. So you'll be in a position to sort of ask questions. So I will kind of go through the tutorials today step by step, but I will sort of copy results over from a folder where I've already finished everything up at appropriate moments in time. We'll try and focus on some of the steps which are a little bit less obvious, and then if anyone has questions, interrupt me at any time. So don't feel the need to wait to the end or something like that. This should be an interactive discussion. All right, so let's go ahead and get started. I'm going to assume that you've downloaded the data already. The first thing we do here is run the project manager, and then we need to import the data into a project. So this is very much like the single particle concept, where you have a project folder, all the data lives in organized subfolders inside the project folder. So I've made an empty folder here called tutorial tomo data fol 2. It's nothing in it right now. There's another one without the 2, which contains the finished refinement that I already ran. So if we look at what it looks like, so the completed folder looks like this. Right, so we've got a folder for tilt series, for tomograms. These are refinement runs. I ran 2 different refinement runs. This was for making an initial model. Then we've got, the boxed out particles, both the 2D, which are the sub-tilt series, and the 3D, which are the reconstructed individual 3D particles. Sets as usual. And I use the deep learning particle picker, which we're going to talk about here. So I have a folder called neural nets, which is where the results of that lives. So again, I'm in this empty folder here right now. So I'm going to run E2 project manager. And we'll get this standard window, which everyone's probably familiar with at this point, up. And raw data, import tilt series. And then I'm going to browse for the original tilt series. So these are the files. If you unzip the zip file, which is provided, you'll get a README file, and you'll get these MRC files. If you download the small version, obviously you'll only get 3, not 4. But these are the original MRC tilt series stacks. So we select that. We don't need to give it a raw tilt or an MDoc file here. We're just going to specify parameters later on. So if we look at the tutorial, we do want to specify angstroms per pixel. Make sure you pick the right one. If you use the small one for the large data or vice versa, you'll have all sorts of funny things going on with CTF. So since I'm using the large data here, we'll use the 1.97. Now I actually skipped the step here where I edited the project. I probably shouldn't have. I'll go ahead and do it now, even though it won't have much effect. Say edit project. Particle mass doesn't really matter for this process. I'll put something in there anyway. 2.7, 300, and then it was 1.97. The only thing this really does, filling in these project parameters, is sort of fills in defaults for you in these other forms that you go through when you're doing the processing. So it just tries to help you make sure you don't make any mistakes when you're processing later on that you have to then go back and redo.
Steve?
Yeah.
Hi. Do you work with at any point the raw frames, or are these assumed to be aligned by Motion Core 2 or whatever?
We assume that you've already processed your tilt series into a stack of yeah. We don't do anything with the raw frames directly here.
Thank you.
I for a long time we did try to do our own sort of Motion Core 2 style thing, but Motion Core 2 works pretty well. The IMOD alignment also works pretty well. So we haven't gone back and done much with that recently.
Okay. And if you did try to work with the raw frames, and do you notice that, or do you find that the tilt series, because they're such lower dose per tilt, and then thus per frame, does that affect the alignment?
The ability to align them.
I think to align them.
Yeah, I'm sure it does. I mean, I wouldn't try and do like sub-region alignment or something like that with a tomography subtilt series. I think when most people do it, they don't fractionate nearly as much as you do a single particle. You may have like 40 frames. When you're doing the subtomogram averaging, usually it's like 5 or 6 or 7 frames or something like that.
And they're much lower dose.
Yeah. So
Okay.
I mean, I have seen that when you're at higher tilts in particular, sometimes you'll have a lot more drift, and it can certainly have an impact. You can certainly get some improved results out of doing the movie alignment, but obviously it takes a little extra effort to do.
Yeah, thanks.
Yeah. Okay. So we've got angstrom per pixel set. We don't need to invert. We just say import tilt series. Now, one important thing to note here is that in the single particle pipeline, we do everything with where higher density are brighter white colors, more positive values in the images. In the tomography pipeline, it's conventional to use negative density for whole raw tomograms. So we adopted that convention since otherwise people in the tomography community just didn't like it. Said, oh, wow, what's this? The particles have the wrong contrast. So for the whole tomograms, particles have negative contrast. And then when you box out the particles and work with the individual particles, then they have the positive contrast that we typically use with single particle analysis. So I'm just saying, if you have these tilt series which were collected with the normal sort of darker is denser contrast that you get out, leave them that way. Don't invert them. If you want to use like these raw tilt files or the MDoc files as part of the import process, that's supported. And it's supported in such a way that you can actually select multiple files as long as you have the raw tilt files or the MDoc files named accordingly. You can just provide a folder name where those files live, and it will try and find matching file names for you. But it's important to note that very often you get like these MDoc files out after you've done an IMOD refinement, but then when you look at the tilt series that IMOD has produced, it's the stack file, it's already been sorted in the correct order. So if you import an MDoc file and the stack file is already in the the minus 45 to 45 order or something like that, then it will reorder them again and it will put them in the wrong order. It's easy to diagnose when that has happened, and we'll take a look at that later on. But just make sure if you tell it to use an MDoc file or a raw tilt file, make sure that the tilt series that you're giving it up here in files actually agrees with what those files say.
Actually, so Dr. Luck,
yeah.
sorry, can I? So I was helping Dr. Baldwin and Robin with reconstructing a tilt series, and I noticed when I just did not send the MDoc, they reconstructed correctly. So I'm assuming then probably what happened is what you're saying is that it's not necessarily going to be sorted in the right order. The MDoc, if you go to the Browse tab and select all the MDoc files you need, and then go to the Browse tab for the tilt series and select all the tilt series you need, they're not necessarily going to be read in the same order that they could find. Is that what you were essentially saying?
So I'm saying, so when if you run if you run serial EM and collect your data that way, the order it collects them in is what it documents in the MDoc file.
Right.
But then when it generates an output tilt series, if you generate a tilt series in a single stack, by default, it reorders things for you, or at least that most of the files I have seen are already reordered for you. So they then don't match the ordering that was identified in the MDoc file in that situation. So you can just look at the raw tilt series, right? So if we go here and open the file browser and let's see, Tomo full.
And yeah, okay.
So if we just open up one of these tilt series, there we go, and zoom out a bit here. So this is starting with the first image in the series. If I just hold down up arrow, then we can scroll through it in sequence, and you can see it's not aligned yet, but you can see that it looks like everything is in the correct order. You don't see things jumping around. So if you do a dose symmetric tilt series, -0, then -2, +2, -4, +4, etc. Then when you go through this tilt series, it won't look like a smooth sequence. It'll look like it's jumping back and forth rapidly, right? So if it looks like it's in a smooth sequence like this, and before you've imported it into EMAN, then you should not give it the MDoc file.
Right.
Yeah, that's all I'm saying.
Yes, and yeah. Okay.
Yeah, I know you got bitten by that when you were a rotation student, right? So,
yeah, well, no, and I guess that's what I was just wanted to communicate to anybody else. Exactly, just as the summary of what you said. If it looks weird, just don't give it the MDoc. Yeah, that's okay. Yeah.
And it's even more confusingly, right? If you do give it the MDoc file and it does sort them in the wrong order, the tomographic reconstruction will still kind of succeed. It'll just be completely wrong. So then you get this reconstruction and it'll look really funny and you won't know what's going on. You say, oh, it kind of like failed or something. Yeah, if you see a failure in the 3D reconstruction, usually it's because you got the tilt series messed up.
Gotcha.
But it's a very easy thing to check. So, all right. So once we've selected these files, let me see, was there anything else we said in the tutorial here? Oh yeah, the default compressed bits that it sets here is 8 bits. 5 is safe and takes less disk space and less time and stuff. So the paper on this was finally published a couple of months ago. I don't remember exactly when it came out, but this paper describes and tests how many bits you need to use, how many bits you need to retain in your raw data to get good reconstructions. And the conclusion is for single particle analysis, in almost every case, you can get by with as few as 3 bits and still get absolutely perfect high resolution 3D reconstructions. It has no impact on the refinement. But if you want to be really safe, if you retain 5 bits, that's basically guaranteed to have no impact on anything. 8 is really safe.
And I think actually that it was either Richard or somebody else in the MRC land that originally said that actually 4 bits was sufficient also, but that was like 20 or 30 years ago.
So about 20. I think the guy you're talking about was actually from Sweden.
I don't remember. It was somebody.
Yeah, there was. I don't remember exactly who it was, but I remember like 20 years ago, someone visited from Sweden, and we had this long discussion with them about how many bits you really should need to keep and stuff. And nobody really was willing to buy into his arguments. And it's one of these things that no one wants to actually take the time to test.
I'm glad you did. That's great.
So the motivation for writing that paper was the paper that came out of NYSBC on JPEG compression, right? Where they said that you should just store JPEG images, and they're probably good enough to get something, even if they're not perfect, which is a kind of true statement, but there's all sorts of other nasty things about it. So anyway, the paper sort of started as a don't use JPEG paper. But then we also covered all of this stuff. Anyway, so
okay, great, thank you.
It is absolutely safe to use 5 bits when you're importing your raw tilt series. The only caveat there would be if you're doing something like room temperature TEM or something like that, where you have really high contrast in the images. The low number of bits that you need to keep is reliant on the fact that the images are very noisy. And the noise actually doesn't seem to make a lot of sense, but the noise gets you more, provides bits for you in a certain sense. Read the paper if you want to know more. So let's see, anything else? Copy, no, that was it. Okay, so make sure you set the apex here. Later on in the processing, you can just specify the apex as -1, which will use the value from the files. But when you first import the data, you want to make sure that it's set right, because otherwise it won't know. It'll try and use the value from the header of the image file, but very often in those MRC stacks, the header value does not contain the right apex value. So, all right, so we launched that. Shouldn't take very long. Again, you can open a little task manager here and sort of see when things finish, although it's on other than Linux, it doesn't always finish correctly. So you can watch what's happening in the console and sort of see. So you can see it's on the second one now. All right, so it's got a couple of them imported now. It's getting on to the next one. So next step is to do the tilt series alignment and tomogram reconstruction. With the small data set, this is pretty fast. It only takes about 10 minutes. Even with a large data set, it doesn't take very much longer, but we don't want to spend a long time, 20 minutes of the tutorial just waiting for the tomography reconstruction to finish. So I will launch one of them, and then I'll copy the data for the others over. Or at least we can talk about the parameters. Maybe I'll just copy the results over. Anyway, so that finished. You'll see we now have a tilt series folder, which contains the same files, but they're now in HDF format instead of MRC format. You'll notice that this tilt series is now about 450 megabytes. And if you look at the original MRC stack, wherever it went. They were 2 gigabytes or 2 to 3 gigabytes each. So we got a considerable compression, file size compression out of reducing the data down to 5 bits. Okay, so we've got our tilt series folder. I am going to, let's see. Well, info. Actually, I'm going to do this. So I'm going to copy the info folder, since that contains all the alignment parameters and stuff, and I'm going to copy the tomograms folder into my project here, and that just contains the reconstructed tomograms. So this is what the folder should look like basically after you finish running the next step in the process, which is this tilt series alignment. So let's take a look at those parameters at least. So 3D reconstruction, reconstruct tomograms. You cannot run the CTF estimation until after you've done the reconstruction, because it won't know the geometry of the tilt series properly until then. And there can be sort of an iterative process here if you like. Now, just like the single particle pipeline, if you check the all tilt series box, then it doesn't matter what you put in the box up here. This can be completely empty, or you can have stuff there. This, if it's checked, will override it. And basically, it'll process all of the files that it finds in the tilt series folder, if that's checked. So now here, you need to either specify the tilt parameters or provide it with raw tilt or MDoc files. Again, you don't want to, if you've imported the tilt series and use the MDoc file to get all the tilt series in the correct order, and then you specify an MDoc file again here, then it's going to reorder them again. So you don't want to use the same MDoc file more than once in the pipeline if you're going to use it at all. The raw tilt file you can use here, assuming it matches the order of tilts you've got. Most of the time, you're going to be dealing with a fixed tilt step. And you can just put in the fixed tilt step here. And if you'd like, you can specify which ID number in the stack starting at 0 corresponds to the 0 tilt image. You don't have to do that. It's not going to hurt anything if you don't do it per se. But if you do specify that, then it'll make things, consider that image to be flat. Well, it can hurt things a little bit. If the 0 tilt isn't somewhere near the middle of the tilt series, then when it does the defocus estimation later on, that could get messed up. However, of course, you could have a bent grid, and the 0 tilt image may not be exactly where it's supposed to be anyway. So there are caveats in all of this stuff. The assumption that it's going to make, if you just leave this as -1, is that the middle image in the tilt series corresponds to 0 tilt, and it's probably close enough to true for most tilt series that it's okay. If you are doing like a lamella, and the lamella orientation is such that the tilt that you're doing in the tomography is in the same tilt direction as the tilt of the tilt angle of the lamella, then you might want to try and compensate for that here or something like that. But these are all very data specific sorts of issues. So the bottom line is, if you think you can do a better job than assuming the middle one is 0 tilt, you can try and do that. If you're going to specify a fixed tilt step, then there's no reason to use the raw tilt file. In this case, I think 2 degrees is correct. Yeah, 2 degrees is correct. The other thing you would need to specify normally is, actually, sorry, you don't normally need to specify it. So normally the tilt axis is going to be automatically determined by the reconstruction program. So it can figure out where the tilt axis is, and it'll get it within 2 or 3 degrees, which is good enough for the tomography reconstruction. The only problem with that is that it can be off by 180 degrees. So if you can figure out what the correct tilt axis to use for your specific microscope and detector, you should put that tilt axis in here. If you don't know what the correct tilt axis is, you can just leave it as determining it automatically. And then in the later steps, there are some things we can do to check it. In the tutorial data, we know it's -4, so we're just going to put it in here for convenience, and we can still go through the steps where we check the handedness later on. It's just that since we specified it, it won't be causing any problems. Okay, most of these parameters we don't need to do anything. So tilt axis we're going to put at -4. Tilt step is 2 degrees, and clip Z we're going to change here 96. All right, well that's the default value that we've got here. Oh, that's the reason we've got all the right values filled in here is because I copied the info folder, which contained the last settings that I typed, which were the settings that I typed when I ran this program previously. So we're seeing the values that I used when I went through the tutorial before. So everything should already be set the correct way. You do want to specify the number of threads available on your machine. You can, if you have a 16-core machine and it has 32, it says it has 32 threads and 16 cores, you do not want to specify 32. You want to specify 16, maybe 20. The hyper-threading that's available in modern CPUs is useful for things like word processing. It's not very useful for things like image processing, where you're really pushing the processor hard. So you can get a little bit of benefit out by specifying a number larger than the number of physical cores in your machine, a little bit larger, but you won't get much benefit out past about 25% increase. I know we talked about that with single particle data, but we've got a few new people here today. So anyway, so number of threads. The machine I'm working on has 8 cores, and we'll just say 8 there. Let's see, patch track. Okay, so patch track is down here. All right, when you do a tomographic reconstruction, this is a fiducial-less refinement, but it still uses landmarks. We use a term different than fiducial because when you say fiducial, people are usually referring to gold fiducials, which you specifically added to the physical specimen to act as markers when you tilt the specimen. So we're not talking about the need for having specific fiducial markers in the specimen. When you use this tomographic reconstruction scheme, it's basically using any high contrast features that it finds in the image as landmarks. The landmarks that it's finding do not need to be spherical or anything like that. Any shape is fine. They're not being used in the same way that fiducials are used in a fiducial-based alignment algorithm. They're being used in an iterative scheme along with 3D reconstruction. It's a complicated process. I have a little talk which explains how the 3D reconstruction process works, but we're not going to take the time to go through that today. The key point is that you'll see some terms here which sound like they're doing sort of fiducial-based alignment. It's not fiducial-based. It's a different scheme. And here, this is another term, patch tracking, which you may have seen in previous generations of fiducial-less alignment in cryo-ET. So, 15 years ago or whatever, there were algorithms out there which said, we'll use patch tracking instead of fiducial-based alignment, and then we can do fiducial-free. So the patch tracking we're talking about here is a form of 3D patch tracking, not the sort of 2D patch tracking that was used 15 years ago. So it's really a completely different sort of thing. If you set this to 0, it will just use landmarks to do the alignment. And this was the only thing that we had available a couple of years ago when we first published the pipeline. And for 90% of data sets with 0, that works absolutely fine. If you have a data set that's a little trickier, it's got a lot of jumping around in the tilt series, or it's got some funny contrast, it doesn't have any good high contrast features or stuff like that, then sometimes the patch tracking can really help. And it doesn't take very long to do. And it's in our experience, it's never harmful to do it. So we usually just say, go ahead and set that to 2. and it acts as sort of a pre-processing step to the whole pipeline. It'll make things take maybe 10%, the whole process take maybe 10% longer, something like that. But if you have a marginal data set or something like that, it'll usually fix up the problems. So if you still have problems getting your tilt series with your own data to align with patch tracking set to 2, then email me about it, and we'll take a look and try and figure out what's going on. I have found very, very few data sets which are good data sets which won't align properly using this procedure. Now, I say good data set, that means that when you collect the tilt series, it doesn't jump by 3/4 of the frame size in the middle of the tilt series or something like that. You need to have a tilt series where, you know, each frame is within, you know, 25-30% of being aligned to the other frames, or you'll have so much missing information that the tilt series, you know, isn't really very usable. You can still try and get something out of tilt series that have a lot of jumps, but you know, it won't work nearly as well as you know, good tilt series. So,
Steve,
yep.
This is the parameter that turn off the 3D alignment in the tilt series, or
No. This turns on a pre-processing step, which tries to roughly align things before it uses the normal algorithm.
oh, I see.
It's not a replacement for the normal algorithm. It adds an extra pre-processing step. If you say 1, it'll do 1 iteration of it. If you say 2, it'll do two iterations of it. It's usually there's really no reason to go beyond 2 normally. So normally we just set this to 2, and it will always get used, and it shouldn't make things worse ever.
Okay, got it.
Okay, so there are other options here. We might as well talk through them. Let's just take a look. NPK is the number of these landmarks that it uses when it's doing the fine refinement, the fine alignment of the tilt series. Normally you don't need to change that number. 20 is a pretty good value. Tilt keep is basically saying it'll pick the 10% of the tilts which seem to have the worst quality, the worst alignment, and exclude those from the final tomographic reconstruction. You can set that to 1 if you don't want to throw any of them away. Throwing away 10, most tilt series have, you know, a couple bad tilts, particularly at the extremes. It's not geometry based, it's quality based. So if, you know, tilt number 5 is, you know, the worst, if the tilt at 10 degrees is the worst one, it'll throw that out and keep the others. Anyway, usually we leave that at something like 0.9. It does not permanently throw it away. It doesn't skip alignment of those tilts. It just excludes the tilt from the 3D tomogram, which is really only used for annotation purposes anyway. So if you go back and do the, when you're doing the subtomogram averaging, it will include all of the tilts again when it makes the tilt series, the per particle tilt series. So don't be afraid of that sort of permanently excluding something. Tilt axis we already talked about and specified.
What about box size, BXSC?
Oh, sorry. That's the size of the fiducial.
Okay.
If you have trouble with your alignment, that's actually probably the first thing that you would try and tweak, would be to, you know, try making that a little bit bigger. So if the things that it finds in your tilt series to use as landmarks are larger than 32, making that bigger may help it track things a little bit better. But again, that's very unusual. So almost all cases, these parameters, the defaults are fine for these 3. The tilt axis is the only one up here that we normally worry about. Also, an iter, this gives you very fine control for how to the sequence that's used when it does the iterative alignment of the tilt series. You shouldn't normally need to change it. Basically, what it does is it takes the tilt series and it downsamples it by a factor of 8. It does the alignments there. In this case, it does that for 2 cycles. Then it downsamples by 4. Then it downsamples by 2, and then it does the full resolution tilt series alignment. When it does the alignment, it always aligns the full resolution data. So even if it's, you know, 10K by 10K, whatever, you know, you get your 6K by 4K or whatever from the K3, it'll use the full resolution when it does the alignment, but the output tomogram is normally going to be downsampled. If you specify 1K, it will output a tomogram which fits in a 1K box. If you say 2K, it'll output a tomogram which will fit in a 2K box. You can tell it to do a full 4K reconstruction if you'd like. There you have to edit the command line here to do that. It's not, you can say 4K here if you'd like. But I will warn you that takes a lot of RAM, particularly if you use a lot of threads. So you want to have probably 256 gigs of RAM if you're going to do the full 4K tomogram reconstruction in most situations. It depends a little bit on the clip Z parameter. All right, clip Z. Normally,
question about the output. So the outsize is 1K. That means it will bring into 1K and doing reconstruction, or it will doing reconstruction and just output with the shrinking.
it does the reconstruction at 1K.
So that means after alignment using the bin1 data, it will shrink into some.
The data is shrunk for prior to putting it into a 3D structure. It does not make a full 4K 3D volume and then downsample it. Otherwise, it would be too memory intensive.
Okay, I see.
I will add that there is a new option here, which was added to deal with the non-square K3 detectors. It was only added fairly recently, I think over the summer, Muyon added it. This auto clip XY option. So if you have an older version of EMAN2 and you try to reconstruct rectangular data, it's going to crop it, and you're only going to get sort of you'll be missing a lot of the region in your tilt series. If you say auto clip XY, it'll look at the shape of the input tilt series, and your tomogram will be more sensible. It'll have the correct shape. Again, it'll still be size, so it's about 1K or about 2K in size. Now, the reason we downsample to 1K or 2K is because the current processing pipeline goes back to the raw tilt series whenever you do anything with individual particles. So when you box out particles for subtomogram averaging, you find the particles in the 1K tomogram, but then it goes back and it extracts them from the original aligned tilt series at full sampling. So the only purpose of these 1K tomograms is to look at the tomogram. If you want to annotate it, you can do that. If you want to box particles, you can do that. And there's really no reason to have the full 4K tomogram for most of those purposes. Now, if your goal is to, say, look at a cell and you have used very low sampling, so if your full resolution sampling was, say, 6 angstroms per pixel or something like that, then if you say 1K, you'd be at like 24 angstroms per pixel, which may be coarser sampling than you want even for cellular annotation. So if you intentionally collected very coarsely sampled, very low mag data for purposes of cellular annotation of a large region of the cell, that would be a situation where you might want to say 4K here, because you're probably not going to follow the subtomogram averaging pipeline anyway. But then you need to make sure you're working on a workstation that has a lot of RAM to deal with the large tomograms. Okay. Clip Z, normally this is just left at the default value, which corresponds to 5/16 of the XY dimensions of the tomogram. But for specific purposes, you might want to set some specific value. The data that we're going to be looking at here, this tutorial data, is single particle style specimen. The ice is pretty thin, so a thickness of 96 will easily accommodate the thickness of the ice in the specimen that we're looking at. This is in pixels. If you're working with, say, a lamella, you want to make sure that the full thickness of the lamella is accommodated by this clip Z value. So you might want to compute how many pixels thick your lamella is, and make sure you use maybe usually if I'm working with lamella, I will first reconstruct the tomogram with about 1.5 times the thickness I think the lamella is. That way, when you do the reconstruction, you can look at one of the side views, and you should be able to sort of see where the edges of the lamella are in the reconstructed tomogram. And then if you want, you can go back and decrease the Z size, although you don't need to. But you want to make sure that that number is at least as thick as the lamella or whatever the specimen is that you're processing. If you make this number thinner than the layer of ice or whatever the specimen is, then the thickness of the specimen, then it will only reconstruct that thickness, and then anything outside that box will get reflected back into the volume that gets reconstructed, and it'll add all this noise and artifacts and stuff like that. So you really want to make sure that the Z thickness that you're using accommodates the thickness of the object you're looking at. These options, the by tile option allows you to tell it to do the reconstruction by chopping the volume up into smaller chunks and then doing the chunks one at a time and then reassembling them at the end with overlapping chunks, overlapping tiles, so there's no edge artifacts or anything like that. This is the normal approach. Normally, you would not want to uncheck that box. I cannot think of a situation where I would want to turn that off. Let's see. If you uncheck no temp, then it will leave behind a temporary folder for each tilt series, which contains a whole bunch of intermediate files, which contain information about which landmarks it picked and all of the different sequential steps that it did during the refinement process. These take a significant amount of disk space, and normally you would only use these for debugging purposes. So if you're having trouble, your reconstructions aren't going the way you intended, then you might reconstruct maybe a couple of tilt series with this option turned off, and then you can look at those folders to try and sort out what was going on. But for routine refinements, there's no reason to uncheck that. All of the metadata about the alignments and stuff like that is stored in info. So if you want to say look at the aligned tilt series or something like that, that's something you can do even without having that option unchecked. The compress bits here is talking about the number of bits to retain in the tomogram. IMOD has used 8 bits for tomograms for 20 years. It was conventional then because you just didn't have enough RAM on computers back in 2000 to do anything with tomograms without, if you used more sampling than that. You are free to use 10 bits or 12 bits or something like that if you think it's going to help, make things look a little bit smoother or something. But for all the purposes, we're likely to use the reconstructed tomograms for 8 bits is fine. Again, we're not taking particle data from the tomogram anyway, so there's really no point. It really doesn't matter if the data is lower quality or something like that, because it's not ever getting used for anything other than visualization purposes. This again relates to the landmark alignment process. So this will allow you to discard some fraction of the landmarks that it picks, and it's a good idea. 0.9 is fine for most purposes here as well. So if it picks some high contrast landmark and it's just not a very good landmark, it's not very self-consistent, it gives it the option to discard some of those. Correct rot is something that you may or may not want to use. If you have something like a single particle specimen like we do here, it's not actually a bad thing to pick. Basically what this will do is it will look at the 20 landmarks that it picked, and it will try and draw a plane through those 20 landmarks, and then it'll make that 0 tilt in the reconstructed tomogram. So if you reconstruct single particle style data and you find that the tomogram isn't flat, so as you move up and down through the tomogram, you see these patches which sort of slide across because the tomogram, the physical specimen was tilted with respect to the XY plane. Correct rot will try and flatten that out, so all your particles more or less lie in the same plane. I think actually that it suggests, yeah, so it wants you to turn that on here if you go through the tutorial. For single particle specimens, this is very useful. For things like lamella or cellular specimens, it's a lot less useful because the landmarks that get picked could be in a bunch of different planes. So the actual rotation you get out of this in thicker specimens with landmarks all over isn't necessarily going to be a good one. So I normally don't use that for cells. Filter res is the final tomogram that it reconstructs will be low pass filtered to some resolution. Tomograms are typically pretty noisy, and usually people want to do some low pass filtering before they try and visualize them. Again, no impact on your final single particle reconstructions. 40 is a pretty good resolution. About 40 to 50 angstroms is the typical estimate people make for what a cryo-ET tomogram will usually have on sort of an individual particle basis. I mean, obviously there's missing wedge and other effects like that, but the things that you can see in the tomogram usually are estimated to have a resolution of somewhere around 40 or 50 angstroms. So that's a pretty good filter value to use. Pause Z is if for some reason it comes with a tilt axis, which is shifted from sort of the center of the actual specimen, pause Z can sometimes help it center along the Z axis a little bit better, but usually it's not necessary. If you have actual gold fiducials present, you can use remove bead threshold to set a threshold value for taking them out of the final tomogram, so they don't interfere with visualization and stuff like that. So it'll wipe them out. I think it wipes them out at the level of the tilt series, so that you don't actually get the funny artifact patterns in the 3D tomogram from the fiducials. If you're using our recommended strategy and not using fiducials, then you shouldn't really need to use that. Since we do the tomographic reconstruction tile-wise, so we chop the tilt series up into cubic chunks, and then reconstruct the chunks, and then we reassemble the reconstruct the chunks in Fourier space, and then we reassemble the tiles into the final tomogram. You can get edge artifacts, as I mentioned before. The default behavior is it does sort of 2 times oversampling. So it basically generates 2 times as many tiles as it needs to generate to fill space. That's enough oversampling to make an okay looking tomogram, but you will still see some artifacts present. What Muyuan, when he wrote the program, he thinks, for the purposes that you're using the tilt series, the tomograms for, it's absolutely fine, and there's no reason to do anything more than that. Because if you do anything beyond that, it makes the reconstruction take a little bit longer to run. However, when other people who are used to, say, IMAD used this reconstruction software, they said, well, the IMAD tomograms look better. They don't have these funny artifacts around. It's like, well, yeah, because the artifacts don't matter for anything. People don't like that logic. And honestly, I prefer to look at tomograms that don't have as many artifacts also. There are 2 different ways you can get around that. One way is, instead of using 2 times oversampling of tiles, you can use 4 times oversampling of tiles. Obviously, that makes the reconstruction take twice as long to run. It's still quite fast. It's still a lot faster than doing it in using back projection or something like that. But it will take twice as long to run if you check this checkbox. But it'll basically make the tomograms look really nice. The other option is, instead of making twice as many boxes, you make each box a little bigger. So this takes a little bit less than twice as long, but may still produce a few occasional artifacts in various places. If you're really aggressive, you can actually pick both of those options, and it'll produce very nice, smooth-looking tomograms. It will probably take, almost 4 times longer to run if you do both. Usually we just use extra pad, and that's pretty good, and it takes 1.5 times as long or something.
Okay, Steve.
Yeah.
I have in a completely different kind of pipeline where we're trying to annotate vesicles and find the tops and sides and bottoms of things, and locate microtubules in the cell and kind of get those things.
I understand.
Making tomograms like that, the rap has been that IMAD gives you the best reconstruction for doing that sort of analysis. It'd be great if we could have EMAN that did that that kind of analysis where, you know, you're not going to do any subtomogram averaging. You're going to annotate vesicles.
Yeah.
So if this would make a very good choosing these things that do this way gets you tomograms that are a lot better than the tomograms that are just used for visualization
So I would say if you check, if I were doing a tomogram for that purpose, I would probably use more tile.
Mhm.
I would make sure that my clip Z was set to a nice thickness, which exceeded the size of my object by, you know, a factor of 1.5 or something like that, the thickness of my object by 1.5. And you know, if necessary, I would go up to a 2K or a 4K tomogram, depending on, again, on what the raw sampling of the data was.
Mhm.
And you should get tomograms which are comparable in quality to IMOD reconstructions if you do that. You can maybe get a little extra quality if you use both of these, but it's going to start becoming a little bit more subtle. Now, there will still be some differences, right? We are doing reconstructions in Fourier space, not real space. So how things look at the edge, where you only have like 2 or 3 tilts contributing to the data, it'll look different in those artifactual regions will look different in EMAN versus IMOD. So I guess what I'm saying is you won't get identical looking tomograms, but the quality of the regions of the tomogram, which are good regions of the tomogram, should be every bit as good in EMAN reconstruction as an IMOD reconstruction. Now, there are other things you need to consider about how you're going to filter the tomograms and stuff like that for best visualization. You know, if you use one of the missing wedge filling programs, Hong's deep learning based tool for doing that. Some of the results we've seen from that actually look really nice. Muyuan wrote something using a completely different approach, but also trying to sort of do some stuff with missing wedge filling. So if you're trying to do things like looking at vesicles on the edge and you want to see the tops and bottoms of the vesicles, some of the wedge filling tools can actually make a significant difference for that kind of application. And that's a much bigger difference than you get out of EMAN versus IMOD or something like that. But those tools take a long time to run, and that's
Yeah. Okay. Well, thanks a lot. Because up to now, everyone has, or at least the people that I've talked to, has said, "Oh, IMOD gives you a really good reconstruction, better than almost all of the other ones, but no matter warp or even, you know."
IMOD has been tuned over the years to sort of filter and produce things which look a particular way, and people are very accustomed to looking at things that way, and they think that anything that looks not exactly like that must be worse.
That's not true. Yeah.
I would say it's not. In the cases where people have said, well, here, look at this one, and then look at what I got out of the EMAN reconstruction, I say, well, yeah, you're looking in a region where you don't have complete data, and you can't use the IMOD data, and you can't use the EMAN data. So why do you care what that region looks like, right? And if you look here in the main part of the tomogram, you know, you can see the same features here as you see here, and you know that. Anyway. So I think statements like that are mostly figments of the user's imagination, because they're used to looking things that are flat in real space but have Fourier artifacts, rather than things that are flat in Fourier space but have some real space artifacts.
Yeah. Okay. Thank you.
Yeah. But you know, that sort of thing does make the decision about which software package people want to use. So you know, it's. I'm not saying it's a meaningless distinction. It's a meaningful distinction, but okay. So I've gone through all of these parameters now pretty thoroughly, which we don't really do in the description here. I mean, we talk about them a little bit, but not at quite sort of the depth we just discussed here. Maybe we'll try and get through. I mean, we've been going for almost an hour now, so maybe we'll try and just get through, say, the handedness check discussion here, and just talk about the CTF a little bit, and maybe we'll then finish up for today. beginning to think that it's going to take more like 3 weeks to get through this whole thing, given the amount of time I spent talking about some of this. Right. So once you've reconstructed your tomograms, you should see that you have a tomograms folder. And if we look at one of these tomograms, if we say show 2D for one of the tomograms, we can look at the XY slices. Now, of course, yeah, you can see, look at all these funny edges. Well, that's because we're all the way at the bottom of the tomogram. Once we get up to sort of the middle of the tomogram, oh, look at that. Let's get the full contrast there. So you can see I didn't do anything to get rid of the gold fiducials that are present. There's only a few of them. Those, they don't really hurt anything too much. This is sort of a more typical contrast. Some of what you're seeing here are just artifacts from the Zoom session, I think. I mean, you can see these little sort of square artifacts on the screen here. That's some sort of funny sampling that's going on right now, just in because of the session. Anyway, so you can now see all of the ribosomes there very nicely, so that the tomograms reconstructed fine. Typically, what you would do once you've reconstructed your tomograms is you'd use this tool, evaluate tomograms, and launch that. Now you'll see more parameters here because I copied the info folder from the other project I already finished. So if you do this at the stage that we're supposed to be at right now, you won't see defocus values because we haven't determined the defocus yet. But I copied it already. So this is a good tool to use. It gives you a quick view of each of the tomograms to sort of tell you whether things kind of went right. It just shows you a central section over here. If you want to look at the aligned tilt series, this is the place to do that. You say show align tilts, it'll read the parameters in, and on the fly, it'll generate an aligned tilt series from the unaligned tilt series. So if we open that up, it'll take a second to generate because it's reading the whole tilt series and it's adjusting it. Then we can look at what the aligned tilt series looked like. Now you can still see there are a couple places where there's like a little jump or something like that, and that's actually because there is some out of plane tilt present in these tilt series. And of course you can see the gray edges, which corresponds to the misalignment that was present when the original data was collected. But you can see that looks very smooth, and hopefully if you look at the aligned tilt series, it will always look that way. This is also a good place to launch some of the other tools like the particle picking tool. There are other things available here for like looking at the per tilt loss function, how well the alignment worked on a per tilt basis, and looking at the per tilt CTF parameters and that sort of thing. But we'll get to some of that stuff later on. Anything else? Yeah, so if you say show 2D, that's equivalent to going to the browser and doing a show 2D there. This is just a nice shortcut for that. Let's go ahead and just run Boxer really quickly. We're already going to see the boxed out particles here because, again, I copied the info file that has all the particle locations in it. But we'll see that opens up a couple of windows here. The reason I'm doing this is just so you can see that hang on, let me adjust this. That you can see that they're flat here, basically, right? So you can see that the particle planes here are flat in XZ and in YZ. With this, you can, let me change this. Sorry, I've got a side window there. You can move up and down through the different Z layers there, and you can see all the boxed out particles and the things that weren't boxed out and avoided the gold fiducials and that sort of thing. Anyway, if you click on a particular particle, that will change the slice that it shows here. I will add that Eric recently fixed this. So if there is a problem sometimes if you're looking at, say, tomograms that have really thick slices, if they're lamellar or something like that, where there was a problem being able to adjust the size of the regions here, you'd wind up with really compressed, be really compressed here, and there'd be no way to deal with it. It is now possible to grab the section between here and here and make it larger and smaller, and to grab this one and make it larger and smaller. Sometimes when you first open the program, this line won't be vertical and you have to grab it once and just shift it a little bit to get it to sort of lock in place. But anyway, you can adjust that now. but you have to have a current snapshot of EMAN2 to do that. All right, let's take a look at the next step, CTF estimation. It's a completely automated process, and it's doing a tilt-aware CTF determination. So it's looking at the geometry information that it has about each tilt, and then it's fitting a model of the CTF following the tilted plane. It's not using the sort of strategy that of like boxing out tiles and assuming all the stuff in each tile is going to be the same defocus and stuff like that. It's actually sort of modeling what the defocus gradient should look like, and then comparing that to what it gets from the image. Again, you just normally check this all tilt series box, and then it'll run it for all of the tilt series in the project. You may need to modify this in certain projects. So the defocus range that it uses for the fitting, you can see the default range, you can see it pops up there, is from 2 to 7 microns in increments of 0.02 microns. But if you collected your tomograms closer to focus, these were collected in sort of the 1 to 4 micron range, for example. You need to make sure that this encompasses the range of defoci that exist in your tomograms, or you won't get the right defocuses out, and that would be bad. There is the option of fitting faceplate data. So you can pick a range of permissible phase shifts if you're using one of the FEI style phase plates. Then you probably want to give this some range, because the phase shift that you get changes with time. So you don't want to just fit around 90 degrees. You want to fit, for maybe 10 to 120 degrees or something like that. That will make the CTF fitting take a little bit longer, but it's already a really fast process, so it won't really impact things too much. Seems to work reasonably well. Most of the other parameters you shouldn't have to mess with. Obviously, make sure your voltage and C sub S and such are set correctly. You don't want to run check hand in. So when you run with check hand, it checks the handedness of your reconstructions, but doesn't determine the defoci and save them to the header. So when you're trying to determine the foci of the entire tilt series, you want to run it without checkhand. When you run it with checkhand, you'd usually just do it on 2 or 3 good tilt series. Since we're already at 10:35, I think we'll probably just sort of stop with that today. So the next step that you would do is just run this on all tilt series, and then we'll maybe take a look at the handedness checking stuff a little bit next time. Any questions on the stuff that we've already talked about today?
Yeah,
Okay.
quick question.
Yep.
When you do the reconstruction of the tomograms, what do you look for to get a sense of whether it was completed as best as possible, or troubleshoot, or what sort of things do you check?
Well, usually what you would do after you do the reconstructions is you would use this evaluate tomograms tool. This is sort of the hub you use for answering those questions. First thing to do is to click on the tomogram and make sure the central section looks okay. You'll always see some edge artifacts just because the tilt series, when as collected, was not perfectly aligned. So there's missing information in some orientations. But hopefully the middle of the central section will look okay. If that doesn't look okay, probably something went wrong. If that looks good, then the next thing I would normally do is look at the aligned tilt series. I'm not saying you have to do this for every tomogram. If you've got 1,000 tomograms in your project, you're probably not going to check each one by hand. Well, maybe you will. I did. I had a project with 1,000 tomograms, and I checked each one by hand. But anyway, so the next thing I would do would be to show aligned tilts, and then manually go through a few of the tilt series and make sure that they seem to be smooth and kind of look like everything's going okay. If that all looks okay, then you're probably in good shape to continue a bit. Anything else?
Would you check the plot CTF at this juncture also?
Well, we haven't actually determined the CTF yet.
Oh, right. Oh, yeah.
Um,
True. Okay.
yeah,
Sorry.
we'll talk about that next time.
Okay.
Okay. Well, I think we'll call that a session for today then, and we'll continue next time with the next steps.
Thank you very much, Steve.
Yeah.
Thank you, Steve.
Thank
Right.
you.
Bye, everyone.